Hello, in this video, we are looking at estimating the sum of an alternating series. So recall from the integral test videos, section 10.4, that the error in estimating the sum of a convergent series by the nth partial sum is Rn equals S minus S sub n. So remember, we have a sum which is n equals 1 to infinity of some sequence a sub n, which is a sub 1 plus a sub 2 plus a sub 3 plus so on until a sub n plus a sub n plus 1 plus a sub n plus 2 plus, and we can keep going to infinity. If I just take these first n terms, this is Sn. This is the nth partial sum. So that means everything else is that remainder. And S equals S sub n plus R sub n. So R sub n equals S minus S sub n. And we had this remainder theorem introduced to us in section 10.4, which was the integral test. And we got an estimation theorem before. We have one for the integral test. Which said, if we have a function that is decreasing, positive, and continuous, then the remainder of that sequence is between two integrals. The remainder of the series is between two integrals. And this was if a sub n equaled f of n for values of n. So we have the integral test estimation theorem that had these properties. And we did not have anything for the comparison test, but we do now have something, or we will have something, for the alternating series test. So the alternating series test has an estimation theorem that says if S is an alternating series, or the sum of an alternating series, where the sequence is decreasing and the limit of the sequence is 0, then we're going to have a property. And the property we're going to get, we're going to describe based on why this proof or this test works. So recall from the first video of this section where I could find the sum of a series by taking those partial sums where I'm adding something and then subtracting something and then adding on and subtracting. And since these are going into 0, we're narrowing in on the sum because this is my first partial sum, this is my second partial sum, third, fourth, and so on. And we're narrowing in on this sum. So I'm going to think about what about as n increases. So let's take this picture and basically zoom it in and say, I have my sum here. And at some point, I have taken my nth term of the sequence and subtracted it. And then I've taken my n plus 1 term and added it. And it's going to go past the sum, but right here would be that nth partial sum, right? If we're following the pattern of this, the end of the arrow represents that nth partial sum. So this is the nth partial sum, and here would be the n plus 1 partial sum. We know r sub n equals s minus Sn. That is the definition of the remainder. But using this number line as reference, s minus Sn is this distance. If I take s and I subtract Sn, whatever this distance is r sub n. Why are we worried about the nth partial sum or the next term? Why is that even part of our picture? Because so far we haven't used it. It's because based on this theorem, we can relate that next term and the remainder together. The next term is going to go past the sum, meaning the next term is bigger than the remainder part. So that is the statement. Then the absolute value of our remainder is going to be less than or equal to the next term in the sequence b sub n. So our alternating series estimation theorem, very short and sweet. Suppose we have a series that meets the alternating series test. Then the remainder is less than or equal to the next term. So actually using this, consider the infinite series -1 to the n plus 1 all over n to the 6th. If we use the sum of the first 3 terms to estimate the sum of this series, what is the bound on the error? This is saying I am taking the first 3 terms together, s sub 3, and s sub 3, not going to calculate it out, but I'm going to write out what it would look like. We'd have 1 over 1 to the 6th minus 1 over 2 to the 6th plus 1 over 3 to the 6th. And we're wondering if I actually found that value, how accurate is it? We could find that value with a calculator. So if we use the sum of the first 3 terms to estimate the sum of the series, the bound on the error is the remainder. And it's the third remainder. What the remainder theorem tells us is that third remainder is less than or equal to b sub 4. So the next term up. What is b sub 4? Well, b sub n is 1 over n to the 6th. So b sub 4 is 1 over 4 to the 6th, or 1 over 4096. So there is how much error we would have of the actual sum s is somewhere between s3 plus 1 over 4096 and s3 minus 1 over 4096. That is ultimately what we are being told by this remainder term. Now, how many terms of the series do we need to add in order to estimate so that we have an error that is less than 1 over 10 to the 6th? Well, we want our error which is less than or equal to the next term in the sequence, to be less than 1 over 10 to the sixth. The next term in the sequence, which is 1 over n to the sixth, is 1 over n plus 1 to the sixth, just taking n plus 1 and plugging it into our sequence. So we want to find n so that that inequality holds. This implies, taking the reciprocal of these again, n plus 1 to the sixth is bigger than 10 to the sixth. So n plus 1 is bigger than 10, or n is bigger than 9. Because of these strict inequalities, these are not greater than or equal to, but they are less than or greater than. This means we need at least n terms to have the error less than 10, 1 over 10 to the sixth. So we can find very quickly what is our error if I only use so many terms, and also how do I get my error to be very small.